In this module, we will talk about different types of equilibrium constants. In our previous discussion, we derived an expression for the equilibrium constant Kp, which relates the partial pressures of the gaseous reaction participants. For the purposes of this module, we will continue with the assumption that all gases behave ideally. The main goal of analyzing chemical equilibrium is to determine the composition of the reaction mixture, specifically in the gaseous phase when it is in equilibrium. While representing the composition of the reaction mixture in terms of partial pressures of the reaction participants is not unusual, using other physical quantities might be more appropriate. In particular, mole fractions, denoted by X, provide a meaningful way for chemists to describe the composition of a reaction mixture. So, let's express the equilibrium constant in terms of mole fractions. When we take into account all the gaseous reaction participants and their molar amounts, the mole fraction of each gas in the mixture, xk, is simply the ratio of its amount of substance, Nk, to the total amount of substance of the gases present. Recall that our discussion of chemical equilibrium is based on the Gibbs energy framework. It implies that the total pressure of the gas mixture is always equal to the external pressure. The partial pressure of each gas, pK, is equal to the product of its mole fraction and the total pressure P. This relationship shows the connection between the mole fraction and the partial pressure of each gas in the mixture. In the previous slide, we have introduced how mole fractions relate to partial pressures in a gaseous reaction mixture. Now, we will employ this relationship to express the equilibrium constant in terms of mole fractions. The first part of the equation recapitulates Kp in terms of the partial pressures, Pk, of the gaseous reactants and products. Each partial pressure is divided by a standard pressure and raised to the power of its stoichiometric number. Given our understanding of mole fractions, each partial pressure in this expression can be represented as the product of its mole fraction and the total pressure. By doing so, we can factor out the pressure terms. This term incorporates the summed stoichiometric numbers for all gases. We will denote it as delta nu. Essentially, delta nu signifies the difference in stoichiometric coefficients between gaseous products and reactants. Using these relationships, we introduce a new equilibrium constant, Kx. This constant relates the mole fractions of the reaction participants. Kx represents the product of each gaseous substance's mole fraction, each raised to its respective stoichiometric number. Note that just like Kp, Kx is a dimensionless quantity. The connection between Kx and Kp is made evident in the last equation, highlighting the role of pressure and the change in stoichiometric coefficients.